Hello, once again, BC Calc students. We are still continuing with Larson's Chapter 9, Geometric Representations of Power Series. We'll be talking about example number 3 here in just a bit. Prior to that, though, I want to keep you abreast of some operations that you're going to be able to perform with power series. The three that come to mind that we will use quite frequently, given any kind of a function f of x and g of x, represented by the two power series that I've indicated here. You could just simply say, hey, if you ever come across a situation where you want to find or represent a function, not of just x, but of some constant k times x, all that you need to do is just take that k of x and plug it in for what was formerly the x and keep everything else intact around it. So in this case, the nth derivative would just, the nth exponent, I should say, would just be a part of the summation expression. Likewise, if you're going to take a function of x that's already going to be raised to the capital N, you'll notice that I just replace this x with x to the capital N, and what that will allow to happen in the simplification is those two n's will multiply together as the exponent rules dictate. And then, of course, perhaps the most obvious type of manipulation or operation is if you're going to add or subtract two separate functions, all you need to do is add or subtract their indicated power series, and you can do so by performing just the factoring out of the common factor, which in both cases would be the x to the n value. So we're going to be using these quite a bit. And off here to the side, we have, it's a little blurry and I apologize for that, but it's a very important caveat that goes with this particular section. It says the operations described can change the interval of convergence for the resulting series. For example, for this particular addition problem, the interval of convergence for the sum of these two power series would be the intersection of the intervals of convergence of the two original series. And you can probably see that that is indeed what's going on here. I don't know if it's such a big deal to point that out. Of course, you could always use the ratio test, although it might have some pretty ugly algebra involved with it, but that's always going to be a way out in order to find your particular intervals of convergence. But nonetheless, we'll kind of keep that in the back of our mind, and we'll see what happens with our example 3 here. We've got a function of 3x minus 1 over x squared minus 1, which is going to require us to do a little bit of work on initially because it just doesn't have that geometric representation. And if you recall, that's what we're going for in this particular section. We've got this nice, clean summation formula, if you will, a over 1 minus r, that we can use as long as we've got that geometric form to the actual series. And I think what I'll do is just to remind us what our ultimate goal here is to achieve something that looks like this. And maybe we might achieve a couple of things that look like this. So that's what we want. This is our goal. And then, of course, we know that that can be rewritten as a over 1 minus r. Well, if you haven't figured it out already, this particular f of x does require a little bit of a makeover, for lack of a better word, because it just doesn't quite have the geometric look. And you'll notice that the denominator does something very special, and that is it factors into the difference of squares, which would lead us to believe that we could do some further investigation into this particular function and perhaps perform a little bit of a partial fraction decomposition and find out exactly how this thing splits apart. So if we use capital A for the first numerator and x minus 1 for the first denominator, we would have this particular look. And then I can proceed to multiply through both sides by the common denominator, x minus 1, x plus 1. And that will eliminate the denominators from the left side of the equation. And on the right side, if we multiply this a over x minus 1 by x plus 1 times x minus 1, we'll notice that the x minus 1s would cancel. And if we multiply this b over x plus 1 here by x minus 1, x plus 1, we would notice that the x plus 1s would cancel. Next, I've always told my students to use a very interesting technique called the Heaviside method, which just allows you to select some values of x that will allow the a and or the b to disappear. And if we were to focus on the b disappearing, we would see that x being positive 1 would be a great choice. So if x were positive 1, we would just plug positive 1 in for all these x's, and we would of course have 2 equaling a times 2, and of course the b term will drop away completely, and that would lead us to a being 1. And on the other hand, if we were to let x be something like negative 1, we would end up with negative 4, right? 3 times negative 1 minus 1 on the left side would be negative 4, and we would have an a times nothing, 0. A is going to drop out, right? No sense in writing it if it's going to drop out. But the b value is going to be multiplied by a negative 2. And of course, that's going to yield a b coefficient of positive 2. So basically what that allows us to do is to revisit this function that we had initially over here and say, hey, 3x minus 1 over x minus 1, x plus 1, that can be written a little differently. We could write that as 1 over x minus 1. Let me move my equal signs down here just a little bit. 1 over x minus 1 plus b, b being 2 over x plus 1. And of course, you could take a moment and add those two back together, and you would find out that that would be correct. It would give you the original function. And now what we got is a couple of functions that just need a little bit of doctoring up to give them that nice a over 1 minus r appearance, because you recall, this is the ultimate goal. So we'll switch colors here to emphasize the next phase of the problem, and that would be dealing with 1 over x minus 1. I'm going to choose to rewrite this initially as 1 over, I would like to have, if at all possible, these values in the bottom switched. And there's not a problem doing that, but we don't want a positive or a negative 1 leading things off here. We want a negative 1. I'm sorry, we don't want a negative 1. We want a positive 1, as we see up there. But that's going to be an easy fix, because if you just multiply the numerator and the denominator by a negative, that will allow the signs to change in the bottom in a way that you want them to. So we could then see that our a value in this problem would be a negative 1. That's the value that's in the numerator, negative 1. And our r is certainly going to be just the x. Now you want to be really careful here. Don't include this minus sign. The minus sign is part of the package. As you can see up here, the minus sign has to be in front of the r. And this is going to allow us to state our power series form as n going from 0 to infinity of negative 1 multiplied by x to the n. And we're all set to go with that guy. All right, next we'll scroll down here a little bit, and let's focus on our other rational expression, 2 over x plus 1, which we can doctor up a little bit, first of all, by switching the 1 and the x. Good news is that we do have the correct term leading things off, 1. The bad news is we have a plus sign here in the middle that needs to be worked, and that's an easy fix. Perhaps you've seen us do this before in another video or two, but we're just changing that to 1 minus negative x. So from here, no problems identifying the fact that a is 2, r is going to be negative x, and that would cause the summation expression here to look something like this. A times negative x to the nth power. Now all we need to do is put these two guys together. We essentially will add these two summation expressions that are written in red and green into a single summation expression, which I'll do over here. So with the summation as n goes from 0 to infinity of, let's see, we've got -1 times x to the n, not much going on with him, plus, now, I think I might do something over here a little different here. I've got this negative x locked up here inside these parentheses. So what we could do is manipulate that just a tad and bring out a -1 to the n power perhaps. And that would leave us just with an x to the nth power, at which point we got to feel a little bit better about this, because one of the goals in simplifying is to have an x to the n that you can indeed factor out. And that's going to happen in our next step by simply grouping together the -1 plus the 2 to the -1 to the n, which I'm going to go ahead and flip the order again so as to not lead off with a negative. But that's going to be a pretty decent representation of our power series. And we'll go with that. Of course, there may be other ways to write this, but this is going to work for us. Now, as far as determining the interval of convergence for these two particular guys, for this particular summation, I think that if you recall, earlier in the video we mentioned something about the intersection of the two individual interval of convergence leading us to the interval that we want. And I recommend that we try that, because it's going to be a lot easier in this particular case. If you see that the R value here was x, then we just simply need to solve this absolute value inequality expression, which is quite simple. It's all values of x between -1 and 1 exclusively. And if we try the same thing for the other interval, well, let's see, what do we get here? On the surface, it looks like, hey, this is going to be a little different. Let's multiply through everything by a negative, and then we flip our signs and we say, oh, wait a minute, no, it's not different at all. So you're basically finding the intersection of -1 to +1 exclusively, and you get -1 to +1 as your interval of convergence here. So it's a much easier way to go back to the original two. But anyhow, that's your first example of manipulating a power series with geometric representation by using the operations that we discussed on the previous slide. Hope this helps. See you next time.